Mapping the environment in a closed room using a mobile robot. To begin with, I would like to present briefly the plan of presentation. Introduction, mobile robot platform, mobile robot application, verification of robot performance, summary. Robots are designed and constructed in such a way that they can carry out work with a high degree of accuracy and speed, which often contributes to increased productivity and reduced labor costs. Robots have many uses and can help in many areas. One of the groups is mobile robots, which are the subject of this work. Like other types, mobile robots are designed to replace humans in heavy or arduous tasks or those that threaten their life or health. The robots can be remotely controlled, or navigate the environment autonomously, that is without human involvement. Moving can be performed according to pre-programmed behaviors and procedures such as moving along a wall or bouncing off an obstacle encountered in a random direction. Another way the robot moves is through autonomous navigation, where the robot's route is determined based on a map of the environment. The robot uses sensor data to determine its position in relation to the map it has, and then determines the trajectory of movement to a predefined target. Mobile robots are used for a wide range of tasks like exploring inaccessible or dangerous places, carrying heavy and dangerous objects, or even combat. Mobile robots are also used in academic environments for further research on robotics issues. The general development of technology and access to information via the web has meant that robots are no longer beyond the reach of ordinary people and are starting to appear more and more in everyday life and to be used, among other things, for simple household tasks, or as platforms for further learning in fields such as robotics or computer science. The presentation describes the process of designing a mobile robot that creates a map of the environment, and then visualizing this map in a human-readable form. The distance measuring device is the most important component of the mapping robot. It is with its help that the robot can detect obstacles and remember their position. There are several devices available to detect an object and determine the distance at which it is located. The Kinect device, for example, uses depth sensors to create a depth map of the image. The infrared emitter on the left-hand side of the device sends out a light pattern, invisible to the human eye, composed of multiple points. This pattern is then captured by the CMOS sensor. Then, the microprocessor embedded in the controller analyzes the offset of the received pattern relative to the emitted pattern. This technique is called the structured light technique. The camera's field of view is 43 degrees vertically and 57 degrees horizontally. The depth sensor range is 0.5 to 6 meters. The refresh rate of the image is 30 Hz. The device powered with 12V, at a current consumption of approximately 1.08 A. Before building the real robot, a preliminary design was made in the SolidWorks to determine the overall shape and dimensions of the robot. This minimized the loss of material resulting from possibly incorrect platform shape and dimensions. The robot's drive in the form of two DC motors was placed at the front. A gel battery with a nominal voltage of 12V and a capacity of 7Ah is responsible for powering the drive units and the motion controller, which allows the robot to run for several hours on a single charge. The battery was attempted to be placed as close to the drive axis as possible in order to shift the center of gravity and reduce the load on the free wheel mounted at the rear of the robot. An H-MEGA328 microcontroller available on the Arduino Uno platform was used to power the encoders located on the motors and the H-bridge circuit. The Arduino Uno chip itself is powered via USB by a laptop computer placed on the upper shelf of the robot. The Kinect controller is positioned on the back of the robot, on an elevation attached to the upper shelf. This positioning of the device will almost negate the minimum range of distance measurements to be taken. The Robot Operating System, ROS, is a middleware, offering libraries, tools and solutions to support the software development for mobile robots. The main idea behind the ROS is to use the work of teams working on individual robotics issues and integrate them into a single system. The advantages of the system include flexibility. The system can be adapted to any type of robot. Modularity. The code implementing individual tasks is delivered in packages, the use of which is entirely up to the programmer. BSD license. The software is made available for free, can be freely modified and made available again. An extended community contributing to the ROS libraries collections with new developments. Nodes are responsible for the operation of a robot whose software was executed in ROS. They are small programs that run independently of each other and are usually responsible for performing one specific task, for example, setting the speed of motors, reading data from distance sensors, etc. The individual nodes communicate with each other using messages composed of simple integer, float and Boolean data structures. Each message is sent within the topic specified by the node. Individual nodes can publish a topic, publishers, or subscribe to it, subscribers, to make use of the messages contained therein. The ROS master, which gives each node a unique address, and informs them of published topics, is responsible for the correct operation of the system. The Arduino microcontroller must perform the following tasks: controlling the operation of the robot's motors following the commands given from the computer keyboard, reading impulses from the encoders placed on the robot's motors, transforming them into the robot's position in a two-dimensional space and sending this position to the ROS. The task of reading the commands is performed by the motor control function. The function converts the commands issued via the teleop-twist keyboard node into a PWM signal controlling the motors. The task of determining the position of the robot is implemented in the distance count function. It uses the encoder H library to count pulses from the encoders placed on the motors, and then performs calculations to determine the position of the robot in relation to the starting point. The encoder class has to be declared for each encoder before the function loop. The verification of the Kinect controller's operation was to check the correct functioning of the packages responsible for the device's operation and the correct publication of topics to the ROS system. For visual assessment, Revis software was used. When the program was launched, the following objects were added to the display: depth cloud, visualization of the depth map created by the Kinect controller. The topic camera depth image RAW containing the data from the depth sensor was selected in the subscribed topic field in the object setting. Laser scan, visualization of distance measurement. The topic scan published by the depth image to LaserScan was selected in the subscribed topic field. The measurement is represented by points of different color. Closer objects turn red, those far away, towards the violet. Camera, a new window displaying a two-dimensional image based on the data from the subscribed topic. First, the topic camera depth image RAW was first selected in the subscribed topic field, then camera RGB image color displaying the image from the RGB camera in order to compare the resulting depth map with the real image. In order to facilitate the evaluation, the side length of the grid cells was set to 10 centimeters. Based on the resulting images shown in figure, the controller and its supporting packages were found to be functioning correctly. The mapping tests were carried out in the three types of room indicated by the numbers 1, 2 in Figure 3A and 3 in Figure 3B. The points marked P and K, respectively, denote the beginning and the end of the route taken by the robot. The red dots indicate the places where the robot has made a full turn around its axis to collect information about its surroundings. The robot also makes a full turn at the beginning and the end of the route. The resulting map images are shown in Figure 4A, B, C. The bright field represents the free area that is not blocked by any obstacles. The black dots mark the locations where the distance scan from the Kinect controller detected an obstacle, while the gray area is unexplored area, beyond the reach of the Kinect controller. After performing the test and analyzing the resulting map, two occurring problems were noted. The first is the distorted distance measurements, particularly evident in the bottom left hand and the upper right-hand corners of the map due poor illumination of these areas, which affected the quality of the measurements received from the sensor. The second problem is the curvature of the walls resulting from the increasing error in distance measurements from the encoders. The error was mainly influenced by surface irregularities and slippage between the wheels and the driving surface. The final test was carried out in a large living room connected to a corridor and a kitchen. Reference symbol 3 in Figure 3B. The resulting map with the overlaid room floor plan is shown in Figure 4C. The aim of the work was to design and build a robot capable of creating a two-dimensional map of a room, and to make a two-wheeled mobile platform capable of moving in a direction set via a remote computer keyboard. The two-dimensional maps created with the mapping node available in the ROS system contained errors within a predetermined tolerance. In the early stages of the design process, experiments were carried out using, among other things, a Raspberry Pi microcomputer. However, its computing power was insufficient, which led to the use of a large laptop computer, which in turn had an impact on the final dimensions of the resulting robot. Despite the aforementioned difficulties, The ROS system has proved to be a very useful tool to facilitate the management of the robot's software, offering ready-made solutions, which would take a very long time to create from scratch. The popularity of the Kinect system in mobile robotics as a cheaper replacement for LiDAR-type laser scanners has come as a big surprise. Despite its relatively good accuracy, its limitations have been noted. The controller's biggest drawback is its narrow viewing angle, which caused the malfunction of the mapping package developed for long-range laser scanners. The problem was partially solved by modifying the default parameters of the mapping package and reducing the robot's movement speed. The minimum distance that needs to be maintained between the Kinect sensor and the object being measured in order for the measurement to be correct also proved to be a problem. A reduction in controller accuracy in low-light areas was also noted. Another problem was the increasing error in the robot's position determined from the encoder readings due to, among other things, slippage between the wheels and the ground or variable wheel geometry during driving. Here's the list of reference. Thank you for your attention.